Welcome to this edition of Project of the Week. Each week I'm going to recreate a project in Grasshopper that is chosen by my subscribers and followers. This week we will be taking a look at the 3D printed Thallus sculpture. This pattern is based on a differential growth algorithm which typically works to create an ever-expanding curve that never touches itself. This behavior of this particular system is tweaked to enable connections in the curve that create a structural system that bonds large parts through 3D printed technologies. In this tutorial, we're going to use Kangaroo physics to create similar patterns and apply them through a parametric geometry. We'll begin this tutorial with a base curve that will serve as the starting point geometry for our differential growth algorithm. We will then divide this curve into a series of points and then segment the curve so we break it down into a collection of line geometries. I've created a template Rhino file for you all to use for this tutorial, which can be downloaded by all members of the differentdesign.com. So if you're not a member, you can sign up for free and get these files. So I've also got a blank Grasshopper document open that we're going to start with, and I'm going to just begin by referencing in a curve geometry, which is this curve geometry here. I'm going to go and set that one curve, and then I might just turn off this base curves layer so we don't accidentally select or move that. Then I'm just going to go ahead and we're going to divide our curve up into a series of segments. I might just start with like 500 segments, so quite a few, we want a lot. And then we're going to create a line between two points. The first point being, these points in the divide curve, and the second point being a shifted list version of these points. So what we're doing is we're just creating basically almost a lower resolution version of this original polyline. I might preview those guys off for now. So we're going to work with Kangaroo physics. So if you haven't used Kangaroo physics before, check out our meshes and physics simulations course on the differentdesign.com. I'm going to come to the Kangaroo 2 tab, and I'm just going to drop a bouncy solver onto our canvas to begin with. So Kangaroo 2 kind of works in a way where we're going to give basically a series of goals as to how we want to affect this curve geometry, and this physics simulation is going to iteratively run over and over and over to try and achieve those goals. So we've gone ahead and segmented our curve in Grasshopper, and the first goal that we want to kind of apply to our geometry in our Kangaroo physics simulation is to tether that curve to a geometry boundary. In this case, we're going to tether it to a mesh geometry that we specify in Grasshopper. So back in Grasshopper, I'm going to go to my goals on tab and select on mesh, and we're basically going to tether all of these points coming out of divide curve onto a mesh that we specify. The mesh is actually going to be this base surface here, which is this rectangle. I'm going to go set one surface and reference that guy in. And before I plug it into anything, I'm actually going to mesh the breadth because it's, a NURBS geometry. We're just going to turn that into a mesh and apply that into on mesh. I can go ahead and put that into on goals. I'm going to flatten this. And right now, basically, Kangaroo physics is going to run and say, keep all these points on the mesh. Because they're already on the mesh, it's actually not going to do anything, but it's basically just like a setup. But when we start like moving these points and lines around a little bit, just give myself a bit of space. We're going to put all of our goals in this big gap here. So I'm going to create a button. Just for when we want to reset that simulation. I'm also going to make my damping 1.00. We don't want our velocity to weaken as the simulation runs over again. And I'm going to create a Boolean toggle and plug that into the on button. So if I toggle this to true, it'll run the simulation. If I toggle to false, it'll just pause the simulation. I'm also going to give the strength of this on mesh a strength of maybe, I'll make it 1,000. I want it to be a pretty strong force because we're going to have a lot of other forces going on during the simulation. So that on mesh goal will tether our curve to our geometry boundary being that mesh. And the next goal that we want to implement through Kangaroo physics is basically to set a segment length goal. We want all of the segments that we've created, all these lines, to be a certain length apart from each other, a certain length in total. It's going to be a larger length than what you start with because that expansion of the curve will essentially create these really interesting geometrical outcomes as the simulation progresses. So to do that, I'm going to come to my goals line drop down menu. I'm going to select the length goal, and the lines we want to implement are just these lines. The length I'm going to go for, maybe we'll just go for 2.00 to begin with, and we'll leave the strength at a default of 10. The other thing I might just do, coming out of the bouncy solver, we get a bunch of points, so vertices. I'm going to create a NURBS curve from these points. They're basically the simulation points. So we can actually view this as a curve rather than a series of points. So I'm going to plug that into goal objects, holding down shift. We just want them all to come in together at once. And I'm going to reset that simulation. We can, watch this simulation run. So it's trying to expand all of the lengths of that curve that we've got. We could go and live increase that expansion, so you start to get this kind of janky curve. All these lines, these segments are trying to kind of move away from each other based on that distance, and you can obviously update it live. So I'm going to just toggle that off and pause that simulation. And one of the things that we want to avoid with this simulation is the crossing of this curve. So this kind of messy overlap that we're creating here. We want to remove that from our simulation, basically. So we've set our segment length goals, and that seems to be working quite nicely in Kangaroo physics. The next thing we want to do is we want to avoid crossing the curve. To do this, we're going to turn our curve itself into a collision object and tell everything in the simulation, try not to hit this curve itself. So to create this collision object, I'm going to come up to goals colliders, and I'm just going to select the basic collider. I'm going to drop that on my canvas. The objects I don't want to collide with are all these line segments that I'm implementing. I'm going to give it a radii of maybe 1.100. It's basically the smallest distance before we try to move away from this collision. And the strength I'm going to give it is, I'm going to give it a strength of 100. I'm going to plug that into strength. Won't plug anything for ignore A and ignore B. I'm going to put that guy in here, and I might just preview these initial lines off and this initial curve, so we can just watch that simulation live again. So we can go and run that simulation, and you'll see we don't get the overlap that we were experiencing before as much. I'm getting a gap here, so I might just invert that to true for the periodic, so we get a closed curve. So then you start to get these kind of more interesting patterns coming through. You can start changing a few of the settings, and the simulation runs really nicely. Perhaps we could even increase the number of points in our simulation. Oops, I probably should have paused it before I did that. Just hit that reset button. There we go. And you can kind of see, some of those really interesting, strange patterns that come out of this simulation. So already we're creating some pretty interesting patterns through Kangaroo physics that avoid crossing the curve, is making it look a lot neater. But the final kind of goal that we want to implement just in this tutorial in Kangaroo physics is a set angle goal. So right now between each of those line segments, you get this kind of, angle as measured by the arrows here. What we want to do is basically get each of these angles so they're flat, so there's no angle between them. So what we're going to do is we're going to apply a force that basically pushes against the arrows that you see in this diagram and tries to create as little curvature in the simulation as possible. So we can find that goal under goals angle. I'm just going to grab the standard angle component, and we're going to create an angle between, I might just stop running that simulation. We're going to create an angle between all these lines, and we're also going to shift the list, and the angle is going to measure between that itself and its neighboring line, basically. The rest angle, I'm going to copy a panel over. I want the rest angle to be 0. And I want this to be a pretty strong force. So I'm going to give it a strength of 1500. And I'm going to whack that into strength. And then we're going to apply that into our bouncy solver. I'm going to reset, and let's run this simulation. And it'll be a little bit slow to begin with, but you'll start to see that the curvature starts to be kind of limited. I'm going to preview this shift list off. And we get, these kind of rounded, blobby, almost kind of like a bit of a water animation or some kind of liquid simulation. You still see we get a few little overlaps here. I mean, we can go and tweak the parameters to try and avoid those things. Generally, it tries to avoid them eventually, and you start to get these really kind of interesting little patterns. So I might toggle that off. We could increase the number of points. I could make this 2,000 points and really give the simulation a workout. This will of course run a lot slower as a simulation. I'll run it and just see how it goes. Yeah, it's going to take a little bit of time to get going, so very slowly we'll see these kind of bubbles start to appear, and then they'll kind of just go really quickly. There they go. They're starting to break away. And then you start to get these really kind of interesting patterns. So you could go ahead and experiment with different settings, different number of points, different base curves will have a very large effect on the outcomes you get in the simulation itself. But in 2D, that's generally how we would go about creating this pattern. I'm just going to, I'll let it run for a little bit. I don't know if it'll fix that little overlap or not. Perhaps not. I might just pause that simulation where it is right now. Oh, it's pretty close to fixing it. I'll just let it run for a second. And you can kind of see how the 3D printing logic builds into this. Like these kind of distances would probably be the size of your 3D printer's bead, and then they would bond together to create kind of the structural integrity that we see in like the project that we're looking at as a precedent. So I'm going to go ahead and pause that bouncy solve for a second. So in the next part of this video, we're going to create a parametric form to apply this pattern to. And if you don't have much experience with parametric design, check out our parametric design course on thedifferentdesign.com. The form we're going to create will be closely associated with the precedent we're kind of taking inspiration from, but you could really just recreate this kind of pattern that we're seeing generated on the screen on any surface geometry that you're able to create inside of Grasshopper. So I'm going to stop that simulation running again, and I might just zoom out, and we might just move all of this stuff across down here, preview everything off except for that guy, and I might turn off this base surface in Rhino, and we might move into perspective mode. So I'm going to begin by just creating a polygon, and I'm going to give it a radius of 50. Oops. Oh, that's not what I want. 50.00. And the number of segments, I'll just give it, I mean, it doesn't really matter. We could go with 20. It could be as low resolution as you want. You can kind of drag this up. I might actually make it a maximum value of 50. I don't really think we need anything higher than that for the polygon. And then I'm just going to find the discontinuity points of that curve that we've created. Essentially what we're going to do is we're just going to loft between two curves. It's almost like the base logic of this would be if we created a unit z vector, we're essentially almost moving these discontinuity points up by whatever, you know, a vector is. Maybe it's 300. Plug that into there. So, you know, up there. And then essentially creating a polyline through both of these, you know, point situations, and then just lofting between them. So this is a pretty boring base form to start with, but we'll go ahead and figure out a way to make it a little bit more interesting. In fact, I think what we would do is we'd create a NURBS curve, not this polyline output that I've created here. So let's go ahead and delete that, and we'll turn that one into a NURBS curve as well, and flatten those guys coming into there. So it's going to be something like this, but we're going to give ourselves a lot more control. So the first step that I'm going to do is I'm essentially going to try and create more of like an arching effect on the base form. So I want the points that are kind of like towards the ends of the curves to kind of be lower, and then it'll slowly kind of come up and around in a loop and then go back lower again. So let's get started on this by just creating a list length component and coming out of the points there. And I'm then going to create a range. And the number of steps that I want in my range is going to be the list length. But to get it the exact length I want, I just need to go, because that's going to create 13 numbers, and I want 12 like the list itself. So I'm just going to create an expression x minus 1 just in the expression editor there. And that's just going to give me like a range of numbers. I mean, I could go ahead and just for, you know, argument's sake, we could have a look at this move vector with that. So you start to kind of, you know, get from 0 all the way up to here. What we want to do though is we want this to come up and then to come straight back down like that, almost like a loop. So right now we're just going straight up. And the way that we'd go ahead and affect that is we'd create a graph, a graph mapper, plug that in, our range into there, and I'm going to make it a Bezier graph. I'm going to get that guy up there, this guy in the corner down to the bottom there, so it's like, you know, that loop. That's almost the form that we're trying to create. I'll plug that into multiplication, And then we start to get, that interesting loop that we're after in terms of the form. So I might give myself a little bit of space over here, and we can probably go ahead and just group those guys. So that's, how we're creating that little loop in our base form. And the next thing that we want to do is I want this to kind of like taper outwards. So I want these to almost be scaled upwards, and then we're going to add a little bit of a twist onto that as well. So the first thing I'll do is I'll just create a little scale component. This guy can probably come out of the way up here. It's almost like a third stream. So this stream's creating that kind of arching form. This one's creating the bottom curve, and then this one's going to create the scaling and moving out of these middle curves. So I'm going to create a scale. The geometry I'm going to scale is all of these points here. I'm going to scale these from the center point, so I'm going to find the area of this polygon, and I'm going to scale from there. And the factor I want to scale by, basically, we could go ahead and do just a 2.00 to begin with. What we're trying to do here is essentially do something like that. But what we don't want is we don't want this kind of like scaling. We want it to do what it's doing out here on this side, but at these kind of points closer to where the points are quite low, we don't want them to scale out at all. So we might actually go and remap these numbers that we've got coming out of this curve here and just reuse them for this scaling situation that we've got going on. So I'm going to get the values out of here. So this, the source domain is actually going to be 0 to 1 because you can see our domain there in that component there. And I'm going to create a construct domain component. The start domain is going to be 2.00, or sorry, the start domain is going to be 1. So I might actually create a panel for that guy. I'll make him 1. And the end domain is going to be 2. And we'll remap those into there. Oops, that hasn't worked how I want it to because I've got to give it a type domain, and you'll see I start to get that kind of like tapering effect that I'm after there. And you could go and affect the taper parametrically like that. I'm just going to leave it at 2 for now, but you start to affect the form in kind of an interesting way with that domain control that we've created. So now we want to rotate these guys a little bit, so I'm going to go and rotate these scale geometries. I'm going to change the angle to degrees. And then I am also going to give it a negative value just because I want it to, basically if I rotate it currently, it's going to rotate in the opposite way that I want it to. So I'm going to make the angle just about 30 for now. In fact, let's make it 0 smaller than 30 smaller than 90. So we never go over an angle of 90 like a right angle. So I'll make that the angle I rotate by. And then the plane I want to rotate is just that centroid again. So now we could go ahead and plug that into the geometry and you start to get a bit of a twist in this. But the problem that we have with this twist is that we're rotating these 2 bottom points here as well, which is something that we don't want to do. So give myself a little bit more room over here. We're actually going to do a list item from this scale geometry here. And I'm going to create a panel. We're going to get list item 0. So that'll be the first item before we rotate, basically. So that one there. We also want to get the last item as well. So I'm going to go and do a list length. Oops, length component. There it is. And we want to get the last item on that list. So I'm just going to create a little expression coming out of here, x minus 1, because the last item won't be value number 12. It'll be value number 11 because we start counting from 0. So I'm going to plug that into the index there. I'm going to flatten those guys coming in. In fact, let's flatten coming out of here. That would be more intelligent. And then we're going to go and do a replace items component. We're going to basically replace this list of items with these 2 points that we've found here. So those will be the items, and the indices you want to replace is once again that 0 and that 11, and we'll, 0 and then 11, and then we're going to flatten coming into there, and then that will be, our rotated list. So now if we kind of go and do that, you'll see that those base points actually hold in place, and you can get a bit of a twist on the form that's being created in this little simulation here. Okay, so now we want to figure out how we can run this simulation over the top of this surface form that we've created. So we're going to basically marry these 2 algorithms together a little bit. Just make sure that you've got the Boolean toggle switched off in the Kangaroo solver. we're going to do a few things. So the first thing we're going to do is we're going to create a map to surface component, and I'm going to map all of these lines. In fact, I might actually just create a little line container to make it a little bit easier for us to use this algorithm. I'm going to map all of these lines coming out of the line component here into the map to surface, and we're going to create a bit of a split between all of this stuff. That. I'll move that guy over there. And we're going to map from basically this base surface that we created initially. Where is that guy gone? This surface here. We're going to map from that source surface, which is, here. We're going to map all these line curves, which are those guys, and we're going to map it onto this lofted surface here, like that. So we get that kind of starting curve coming into our algorithm. So then we're going to override all of these lines here with this curve here. So this mapped curve is going to be the new curve on this simulation. And then the surface that we're going to actually mesh is going to override that guy. So we're going to run the simulation on top of this new form that we've created. Might go and preview a few things off, just so we've got a clear understanding. If I hit that reset button, we also want to just make sure that the points that we're mapping are coming from this curve here. So I'm actually going to create an endpoints component, and we'll grab maybe just endpoints and override that. So if I hit that button, we should get all of that working onto our simulation properly. So that's the kind of little setup there. We're just basically mapping those lines onto this surface here, onto this lofted surface, sorry, and then we're going to rerun that algorithm. So if I go ahead and run that simulation, we should start to be able to view this iteration on top of, our base surface here, although we're getting a bit of an error straight away. There's a few little kind of overlaps going there, which tells me perhaps we don't have the settings as perfectly aligned as we'd like. I might just Boolean toggle that guy off. So the first thing I might actually just do is just reduce the number of points. Let's try it with 500 points again. And just give that a bit of a reset and see how we go. So it's a little bit better. We still get a bit of an overlap. That's probably just to do with the base curve. So as I kind of mentioned before, the base curve can often have a pretty significant effect on the simulation itself. I've actually got another base curve in here, base curve 002. We could go ahead and input that into this initial curve. So we could go and set that as our base curve. Oops, I should not have let the simulation run. There we go, and then if you run that, you start to get like slightly different outcomes. There's actually a better outcome in this regard. So maybe we could go ahead now and increase, the number of points again to 2,000. Give that a reset and watch, this simulation kind of unfold. And you start to, recreate this kind of really interesting pattern with all this logic that we've embedded through Kangaroo on top of that base geometry. So, outcomes from this, first of all, I'd have a go at playing around with the settings in the base pattern and see what you're able to create for different types of patterns. I think there's a lot of scope to change the parameters in Grasshopper or add, different types of Kangaroo physics simulations. You could also go and try and change the base form and try this on a totally different form as well and create your own kind of unique designs using this kind of simulation logic. Then if you want to, visualize this in 3D, we could go and create like a mesh pipe component, plug in that curve. Take a little bit of time to resolve that. The radius you're going to be wanting is basically the same radius coming out of this collider. So it's almost like that 3D printing radius. And then we could go ahead and preview it. Get a nice white material. I think it might have like a bit of a meshing problem that I've experienced a few times. Just have a look at it in rendered mode. Looks a bit dodgy. So sometimes there's a bit of a rendering error that occurs. It might not happen on yours, but happening on mine. You can subvert this by just like deconstructing the mesh and then reconstructing it. and plug that guy into there, and then you'll get you know, that geometry appearing with some shadows.